Today we're going to talk about continuity, which is a very important concept in calculus for the remainder of the course. And I want you to think about the root of continuity, which is continue or continuous. We've all been around someone that talks continuously. It seems to go on and on forever. There's never a break. There's never anything happening that's unexpected. That's what we think of when we think in the real world outside of math. What do we mean when we say continuous? Just keeps going forever, goes just as we anticipate it to. Well, it has that same type of definition, same type of explanation in math. If we say something is continuous, specifically a function, then the function does what we expect it to do at that point. It's nice and smooth, it stays flat, it does exactly what we expect it to do, and if it does, then we call it a continuous function at that particular point. Mathematically, though, there are three parts to the definition for continuous, and you need to be sure that you know these three, and you're going to hear these over and over quite a bit throughout the year. If we say a function is continuous at a point, that means, number one, the function is defined. That means for whatever the function is, if we put in the number c, then we can get some number out. The limit exists, and we've talked about that. We have to be able to evaluate the limit and come up with a number. This could be evaluating it graphically or numerically or algebraically, and all of those ways should agree if we choose to use all of them to find the limit. And the final piece of the puzzle is that the limit and the function value have to be the same. So you can think of it that the first step says that the function exists. The second says that the function does have a limit, it's going somewhere. And the third piece says the function is going where we expect it to go. We expect it to go to the function value. The limit is where it's actually going, so it's going where we expect it to go. Now, that only talks about continuity at a specific point. What if we talk about continuity on a specific interval? And this is not mean a point a comma b. This is an interval. This means for all numbers between a and b. The fact that there's an open parentheses tells us that it's an open interval. That means that the number a and the number b are not in the interval, but we get as close to a and as close to b as we can. So we say a function is continuous on an open interval, a to b, if it's continuous at each point on the interval. So basically, if we can show that these three steps are true for every point between a and b, then we say that the function is continuous from a to b. Let's look at these graphs and talk about the types of discontinuities. Now, a discontinuity is where the function is not continuous, where the function does something that we don't expect it to do. So when you look at this first graph here, 2 points should jump out at you as being points of discontinuity. Right here at x equals -3 is a point of discontinuity. And right here at x equals 2 is another point of discontinuity. So let's talk first about this point of discontinuity here. And let's look at it in light of the definition. So the first part of the definition says, is f of -3 defined? Is there a function value for -3? Yes, there is a function value. The function value is this point right here because there's a solid dot there. And we're going to say that that looks to be about 0.6. So it passes the first part of our definition. The second part of the definition said, does the limit as x approaches -3 exist? All right. Well, if we look at this function from the left side, the limit, the function appears to be going to a number down here, -0.6 or 0.7. If we look at it from the right side, the function appears to be going to +0.7. So the limit does not exist. Therefore, the function is not continuous. So this one failed at the second prong of our test. The function value existed, but the limit did not, so it's not continuous. Let's talk about over here at this particular point. First of all, is the function defined for for x equals 2? Yes, it is. It's this black dot down here, which looks to be at about 1.3. Second test is, does the limit exist as x approaches 2? Does the limit exist? If we look at the function from the left, it appears to be going to about 0.5. From the right, it appears to be going to about the same place. So we've got the first two parts of the test are true. The function's defined, the limit exists. Are the function and the limit the same? So no, they're not. So this one fails at the third prong of our test, the third piece. No, the function value and the limit are not the same, therefore the function is discontinuous. Well, let's look over here at this graph. What can you tell me about this graph? When you look at it, do you see anything strange? Do you see anything that says it's not continuous? Right here at this point, we have a hole in the graph. Okay? Since there's a hole there, then this is a point of discontinuity. This point, which is x equals 3, gives us a point of discontinuity. This is called a removable discontinuity. Okay? I'm going to try to spell that again because I did not do a very good job of it here. So removable discontinuity. Removable discontinuity, because simply by redefining the definition, if we were to define the function to be this one point with this value right here at this point, then this function would be continuous. So it's a removable discontinuity. Now over here on these other discontinuities, on the first one, what are they? Can the function be redefined to make these two join up? No. So this discontinuity over here is called a jump discontinuity. Okay, because the function jumps from one place to another place. Another name for this would be a non-removable. Non-removable, because we cannot remove that point of discontinuity simply by redefining the function. It's too big of a gap there. The only time there's a removable discontinuity is if there's a hole in it. All right, let's look at this last picture down here. And when you look at it, do you see any points of discontinuity? Do you see any places where the function does something strange? Again, I would expect your answer to be right around this point, x equals 1. There is a point of discontinuity. And that's because the function value is not defined, for one thing, and the limit does not exist. So this one fails on the first two prongs. First of all, first of all, the function is not defined at that point because this is an asymptote. And secondly, because the function limit doesn't exist, it's going up on the right-hand side and it's going down on the left side. So this one has a point of discontinuity at x equals 1. So look at these and tell us what you think. What are the points of discontinuity, first of all? You should find that there's a point of discontinuity here at x equals -1, here at x equals 0, and here at x equals 1. So we've got 3 points of discontinuity. We've got x equals -1, we've got x equals 0, we've got x equals 1. Now, what type of discontinuity is it at x equals -1? Would you say that's a hole, or is that a jump? That's a jump discontinuity because the function jumps from one place to another. Is it removable or non-removable? It's non-removable because anytime there's a jump involved, it's going to be a non-removable discontinuity. What about at x equals 0? The function is going up, looks like towards infinity here, and then it jumps back down. It jumped, therefore it's a jump discontinuity, therefore it's a non-removable discontinuity. What about here at 1? At 1, the limit exists on both sides. It's going to the same point. So here it's simply a hole, and it is a removable discontinuity. Now, some books would disagree with me there. I say it is a removable discontinuity because we can simply redefine the function to be this number instead of this number, and we have a valid function that is continuous. Some books will say, no, this is a non-removable simply because the function's already defined. I disagree with that. I'll differ with the authors on that from book to book. But for the purposes of this class, this is a whole discontinuity, and it is a removable discontinuity because we can redefine it and the limit will exist.